Okay, so for 3-3 notes here, we see some of the same old stuff again, but we do actually introduce a couple new topics. So we'll see air resistance and drag pop up here in the first part of this note, and then the last example that we're going to do is a very, very tricky one. So if there's nothing else that you guys watch, make sure you watch that last example, example 8. Probably a lot of the other examples you'll be able to work through on your own, and it's perfectly fine with me if you choose to do so. But anyway, just summarizing these, I know these are on the example page for you. So things to notice about air resistance or drag: it always opposes the direction of the velocity. It increases in magnitude as the object's speed increases. We'll see a couple relationships for that. But as a general rule of thumb, the drag force increases as the velocity increases. So the faster something's going, the more drag force it's met with. Drag force can get pretty complex, but if we keep the following conditions here, we can actually simplify it. So we'll assume that objects are always moving through the air's surface or through the air near the Earth's surface. The object's size, the diameter, is between a few millimeters and a few meters. So if this was a very, very large object, it would change the drag fairly significantly. So we'll assume that most of these objects are something like a ball or a rock that's fairly small in diameter. And then finally, the object's speed is less than a few hundred meters per second. So that's not really too much of a generalization, but it wouldn't be if it was maybe a plane flying at a very, very high speed. It would complicate drag a little bit more. So we'll keep it fairly simple by assuming these three unless they tell us otherwise. But nothing too tricky on that first one. So then a few other notes about drag. We're going to see in the equation here, right? We're going to see in the equation here, and actually I think I may have scrolled down and missed the equation. So the drag equation that we work with, drag equals 1/2 c rho, which looks like a p, right? And then a v squared. So here's the equation for drag. Again, I think I actually did not photocopy that into this slideshow here. But here's the equation we're going to work with for air resistance or for drag most of the time. A few things to make sure you note about it. So c is the drag coefficient. It's actually very similar to like the static or kinetic friction coefficient. It's usually just a number that's provided to us. It is based on how aerodynamic the object is. So calculating c is not really something we typically do, unless maybe they gave us all of these other measurements. So c, the drag coefficient, usually it's given to us in the problem. The rho here, that what looks like a little kind of italicized p, is the density of air, which we will almost always take to be 1.2 kilograms per meters cubed. And then finally, A is the cross-sectional area, and that is a very important concept there. It's a cross-sectional area. So as an object is falling, for instance, as this sphere here is falling, the area would be just that cross-sectional area of that circle, right? That would be a cross-section of that sphere, right? So A represents basically the surface area in the direction that it is falling. So notice with the cylinder, if I drop the cylinder upright here, the cross-sectional area would be just a circle. Whereas if I drop the cylinder kind of long ways here, the cross-section actually ends up being a rectangle because I have this rectangular plane that can be cut out of that cylinder. So anyway, A depends on kind of the way that we've dropped the object and then whatever the cross-sectional area is. And then finally, v squared here, v is just the velocity. So breaking this all down again, my drag force, my d, sometimes you see that with an arrow on top of it, but my drag force equals 1/2 the coefficient of drag, my air density, my cross-sectional area, and my velocity squared. So most of the time for us, this is going to be the equation that we work with when we see drag or air resistance. We will see another perspective a little bit later here, but again, this will get us started on most of them. Okay, so example 1 here isn't by any means very conceptually difficult. I think it is a good question, though, to introduce a couple of our newer concepts. So the first concept, obviously, is drag, which is we've seen on that last slide, right? And then the other concept is rolling friction versus static and kinetic. And rolling friction is exactly what it sounds like. If you have a wheel, right, or wheels rolling across the surface, then it actually does not have the same amount of friction as a block being pushed across a surface. So if you ever see rolling friction referred to, we calculate it the same way we normally would, right? So my force formula for rolling friction, so I'll call that F sub r, it's still just my coefficient of rolling friction times the normal force. So really not a new equation for us to work with, just a different type of friction than we've seen before. But anyway, this question gives us the rolling friction coefficient. And notice it's a pretty small number. It will almost always be a very, very small coefficient. So my rolling coefficient is 0.02. They ask me to find out at what speed the magnitude of the drag force equals the magnitude of the rolling friction. So I'm going to go ahead and find my rolling friction first. So I've got my coefficient, and then obviously the normal force, well, if it's just going across a horizontal surface, if it's just going across a flat road, which we will assume unless they tell us otherwise, then the normal force we know would be equal and opposite to the force of gravity, right? So this would then just be 1500 times 9.8. So my rolling friction, my 0.02 times 1500 times 9.8. So then calculating that rolling friction, we end up with about 294 newtons. So this question asked me to compare that, right? They asked me to compare when my rolling friction is equal to my drag force, or vice versa, when my drag force is equal to my rolling friction. Well, drag force is in the new equation we're working with here, right? So the drag force equals 1/2 c rho a and then v squared. They're asking me at what velocity, so I'm looking to solve for the velocity. And so the rest of these measurements I have to either find or calculate, right? The big concept here, though, is the fact that now that I've found my rolling friction, I know that that's supposed to be the same as my drag force, right? Because they're asking at what speed does the magnitude of the drag force equal that of rolling friction. So I actually now know my drag force, my D, is 294 newtons. My C, my coefficient of drag they gave me, so that number is just thrown in there, 0.35. Again, my rho is always 1.2 unless they tell me otherwise, so 1.2 kilograms per meters cubed, just the density of air at room temperature. And then my cross-sectional area, well, that's where this first sentence comes into play. They say the profile as seen from the front is 1.6 meter wide and a 1.4 meter high. So in other words, it's basically a rectangle. So the area then is simply 1.4 times 1.6, and that tells me the cross-sectional area is about 2.24 meters squared for my car as it's driving through the wind. So I've got these measurements, and then I'm just looking for the velocity. So at this point, it's no more than just plugging those measurements in, right? So I just take all of those values, again, knowing that the drag force is supposed to be equal to the rolling friction. So 294 equals 1/2 my C, my coefficient of drag, 0.35 in this case, 1.2, 2.24, and then solving for the velocity, right? So just the algebra, and I know you guys are good with the algebra here, so I'll trust that you guys can check this. However, I will write down the final answer if you prefer. So the final answer ends up being about 25 meters per second. So when you're traveling 25 meters per second, that's when the drag force would be equal to the rolling friction. Now, in the context of this problem, what does that mean? Well, here's my very rectangular aerodynamic car, if you will. So here's my car, it's going again. This is actually kind of a confusing question because the drag force and the rolling frictional force, the reason that we set them equal was just to give us a starting point. There's very rarely a significance when both the rolling friction and the drag force would be in opposite directions. So in this case, again, this context doesn't make a whole lot of sense because I'm just happening to say that these two are equal. They don't have to be equal. There's no significance of them being equal. We don't all of a sudden know it's moving at a constant velocity. So it's kind of just an odd context, but the reason that I do like this question is because it introduces both of those new terms and shows that hopefully those two terms aren't too bad to work with, right? Drag force is just a new equation to get comfortable with, and the rolling friction is really the exact same thing we would do with static friction or kinetic friction. It's just got a different coefficient than the others. So anyway, hopefully that's not too bad. Hopefully this first example was pretty straightforward. Alright, I have turned my phone off, by the way, so no more of those nonsense distractions, right? As I'm sure you guys always turn your phones off as you're watching this video, but that's beside the point, I suppose. Anyway, another perspective on drag, and this is actually very common for, and you guys will see a few examples of this with the free response for Physics C, so we'll do a couple of these examples together at some point. But anyway, another perspective of drag, sometimes they just define the force for us. So they may say that the resistive force is simply R equals negative BV, where B is just some constant and V is obviously the velocity. So they may just define this force for you. I've also seen occasionally where they'll just say F equals negative B v or negative kv or whatever value they want to make that. So sometimes they just refer to this as a whole drag here. Now the one thing that I do want you to think about a little bit, the last equation that we saw for drag was 1/2 c rho a v squared. This is defining it as a linear relationship, right? So they do actually take on different formats. This one here would be more of a quadratic relationship, whereas this one would be a linear one. We don't have to worry too much more about that. Just I do want you to recognize that this would be a quadratic function, whereas this would be a linear function. So depending on the context of the problem, depending on which of these they're choosing to use, that may mean that the air resistance or the drag is behaving slightly differently. Again, in this example, it would behave as a quadratic, where my graph would maybe look something more like that, whereas in this case, the drag coefficient would be more of a constant, right? So maybe more of just a linear equation for us. But anyway, the point that I wanted to get to with this relationship, because we do see it pop up from time to time, and really I could do it with either of these two equations, but how would we find the terminal velocity from either this equation or the one we've seen before? Well, the key concept there is, what does it mean to be the terminal velocity? And hopefully you guys remember this from last year. We did talk about it briefly, and probably just a term that you guys have seen, no pun intended there, seen a few times before. But the terminal velocity is really the maximum velocity that an object reaches, right? The terminal velocity is the maximum velocity. So if I take a ball and I drop that ball, eventually in real life situations where there's air resistance, eventually that ball is going to reach a maximum speed, which in other words, if it's reached its maximum speed, what does that tell us about the acceleration? Well, the acceleration, if it's reached its maximum, if it's not getting any faster, that tells us the acceleration would be 0, right? And that's really the key. If I want to find an equation for my terminal velocity in terms of either my r equals negative bv, or in terms of the drag equation that we've seen before, it doesn't make any difference. If I want to find my terminal velocity, the key is the terminal velocity happens when the force of our air resistance is equal and opposite to the force of gravity pulling down. Because only when those two forces are equal and opposite would my net acceleration be 0, right? Would my net force be 0? So if I want to determine an equation for my terminal velocity, well, that happens when my force of gravity is equal to my resistive force. So using the equation we've seen up here, right, using this equation, that would happen when my force of gravity, which is mass times gravity, is equal and opposite to bv. And notice I'm dropping the negative here because the significance of the negative was just that it was opposing the motion. I already know that these two are opposing, so I'm dropping that negative. But anyway, so if I wanted to solve then for my terminal velocity, again, this would be my terminal velocity because that's the only time that these two forces are equal and opposite. So solving then for that is pretty easy. My terminal velocity would equal mass times gravity divided by b. So nothing too crazy with that one, right? Hopefully pretty easy to work through. If I wanted to do it with my drag equation, I could certainly do that as well, right? Nothing much worse than what we just saw, right? It just has a few more variables in it. Again, it would happen when my force of gravity equals my drag force, right? When those two forces are equal and opposite. So my mass times gravity equals 1/2 c rho a, and then my velocity squared. So a little bit more work to solve and isolate for v, but other than that, nothing too crazy, right? So again, just solving for v and then getting from there. So v equals the square root of, I would multiply both sides by 2, so 2mg, all divided by c rho and the cross-sectional area. So either of these, depending on the context, either of these could represent the terminal velocity. But obviously it is very, very important we understand that concept, so hopefully that wasn't too bad. I'm going to go ahead and stop the first part of the video here. We've introduced most of the new concepts for this section, and then in the next part I will try and pretty quickly work through most of the examples, so if you guys need to see any of those worked out, you've got them for your disposal. But anyway, I'll end this first part here.